Hello everyone. Today's lesson is on 7.5, solving linear trig equations. Okay, solving means you have an equation, you have an unknown that you want to solve. But in this particular sections, we are looking mainly on the linear trig equation. That means there's no exponents, right? There's exponents always 1. That's what linear is for. So if you look at example number 1 from the worksheet, so solve for x, and please do always pay attention to the given domain, because trigonometry equation is a continuous function, so it just never ends. The wave of the trig functions will repeat itself one cycle after the other cycle. So without the given domain, then you will have infinite number of solutions, okay? But with the given domain, then your solution has to be within this range. And the most common domain given usually is between 0 to 2 pi, okay? So the first example, 1a, when you have a sine x plus a 1/4 equal to 0. So this is a typical trig equation that you will be getting. And this is a linear because you don't really see any exponents attached to the variable term. So the variable terms here is the sine x, okay? So whenever we're trying to solve anything, we need to isolate the variable term. So this questions I'll be bringing everything else away from the sine x. So I will get sine x is equal to negative 1/4. Now, with that, think about, so sine x, sine of an angle, is equal to this ratio, and a negative ratio. I hope everyone still remember, according to the Cash rules, that there's always two quadrant that will give you a positive or a negative ratio. So if you look at the Cash, okay, then we will know that sine will be negative in quadrant 3 and quadrant 4. So it's very important that we first find the related acute angle first. So I still using beta to be my related acute angle. So I'll be taking the inverse of the sine, but only put in the positive ratio, okay, because related acute angle is always positive, remember? So that, because this is not a special angle, so I know that this is going to give me some decimal in terms of radian. So again, we don't use degrees anymore. So when it comes to the radians measures, so I would be rounded to the questions asking for 3 decimal places. So I will be rounding this as a 0.253. But of course, you need to put in RAD at the end because this is the angles in radian measures. Okay. Once we know the related acute angle, then I know that the principal angle x now is going to be equal to pi plus the beta. So I'm going to add the pi with the 0.253 rad. So you will be getting, and you will be getting approximately, it's going to be equal to 3.394 rads. Okay, so this is going to be the angles in quadrant 3. Now, when it comes to the quadrant 4, my principal angle x is going to be equal to 2 pi minus the beta. Okay, so that you will be getting a 2 pi minus a 0.253, and so you will be getting approximately is a 6.031. Okay, if we are going to round it to 3 decimal places. Well, usually I'll be rounded to 2 or 4. according to my rounding rule, but because this handout does require to round it to 3 decimal places, and that's why I'm rounding into 3. Okay, so this will be the answer for the part A, and so quickly look at part B. You have a tangent x plus 9 equal to 1. So I'm going to isolate the variable term tangent x on by itself, and so you bring the plus 9 over, so it becomes a 1 minus 9. So tangent x is going to be equal to a negative 8. Okay, so same thing. We know that according to the CAS, tangent is negative in quadrant 2 and in quadrant 4. So first I need to find out what my related acute angle is. So again, I'm taking the beta, so negative of the tangents, but I put in a positive 8 here. Okay, again, I'm going to round this into a 1.446 rad. Okay, and so over here, when I try to solve for the x, I know that in quadrant 2, my x is going to be equal to pi minus the 1.446. So that will give you approximately 1.695 rad. Okay, in quadrant 1.695 rad in quadrant 2, and then in quadrant 4, x is going to be equal to 2 pi minus the 1.446. Then you will be getting approximately 4.837 rad in quadrant 4. Okay, so each of this question will have 2 solutions for x, and because the ratio is a negative, while even if the ratio is positive, within the 360 degree, you always get 2 quadrants for positive or 2 quadrants for negative. Okay, now the next example is example 2. Again, find the exact solutions for x between the 0 and 2 pi. So when it comes to the exact, so that means most of these questions, you must be dealing with the special angle. So one of those 3 special angles. So it's either the 45, the pi over 4, or the 60, the pi over 3, or the 30, pi over 6. Okay? Now, example 2a, I have a root 3 times the cotangent of x minus 1 equal to 0. So again, cotangent x is my variable term. So I'm going to bring everything over and only leaving cotangent x on the left-hand side. So I should have a 1 over a root 3. If you remember those special sine length for the special angles, so 1 over root 3, so that basically, or you can look at this. Well, whenever you have the reciprocal, you always have to think about the primary one. So a tangent x will be the reciprocal of that. So it's a root 3 over 1. And a root 3 over 1, if you remember, or you can just use your calculator, taking the inverse of the tangents by putting in root 3, and you will see that your angle is 60 degree. Okay, so under the degree mode, you can tell that this is going to be a 60, but if you put in the radian mode, then you won't know. But by just looking at the sine length, if you have the opposite root 3 over the adjacent one, then this has to be a 60 degree. So related acute angle is 60 degree, pi over 6. And because the ratio is positive, so we know that tangent is positive in quadrant 1 and also in quadrant 3. Now in quadrant 1, the principal angle x is always equal to the related acute angle. So that means x is equal to pi over 3 in quadrant 1. Okay? But in quadrant 3, the principal angle x is equal to a pi plus the related acute angle. So it's a pi plus the pi over 3. So when you add them, common denominator, you will get a 4 pi over 3. Okay, so because I'm having this in the exact form, so I don't need to put in the RAD. Okay, so that is the main difference between example 2 and example 1. So quickly look at example 2b. Again, the variable term is cos x. So I'm going to isolate cos x by itself. And here I have a negative 2, but plus 1. But I still need to divide it by the root 2. So you have a cos x is equal to a negative 1 over root 2. Okay? And if you remember those adjacent side length and the hypotenuse side lengths as being the 1, the negative 1, and the root 2. And so you know that this related acute angle, okay, you can take the negative 1 of that, but don't put in the negative. But the adjacent side length 1 and the hypotenuse root 2, then very quickly you should know that your angle, your related acute angle is the 45, the pi over 4, okay? And because cos x is a negative ratio, so a negative ratio for cosine is happening in quadrant 2 and quadrant 3, okay? Because it's a negative. So my principal angle x really in quadrant 2 is a pi minus the related acute angle is pi over 4. So common denominator, you will get 3 pi over 4 in quadrant 2. And in quadrant 3, your principal angle x is equal to pi plus the related acute angle pi over 4. So common denominator, you will get a 5 pi over 4, okay, in quadrant 3. And this is in quadrant 2. Okay? Now, quickly look at example number 3. Okay? We're doing the same thing, but now when it comes to the mixture of like sine and cosine, and when you have more than one, then you have to also think about the you also have to think about other strategies, such as to make it turn into like a double angles or the compound angles. Okay, so in this case, really, if you multiply, think about that. Okay, I still have the given domain as x between 0 and 2 pi. Okay, in exact form, that means likely this question is going to be one of those special angles. Now, if you recall, sine x cos x, okay, is kind of a similar to the double angles formula. If you remember, the sine 2 theta is going to give you, if you recall, sine 2 theta is going to be equal to 2 sine theta cos theta. So what I'm missing here is the 2. So if I multiply, or if I multiply 2 for both sides, okay, then I will make that into a 2 sine x cos x. Over here, I will get a root 3 over 2. Okay, just to think about that, like I cannot solve when there are more than one variable here. So either I isolate the sine x, it won't give me anywhere, or if I just isolate the cos x, it won't give me anything as well. But the reason why I'm putting this like the double angle, so that I can combine this. I can say, well, this is my sine 2x. Okay? And now it seems to me that like this is only a one variable that I have to deal with. Okay? One variable that I have to deal with. Now, if I replace this, okay, if I look at this as one angle, sine of a theta is equal to root 3 over 2. Well, then, of course, a positive ratio, I know that according to the CAS, I have it in quadrant 1 and quadrant 2. That is positive. Okay? Let's not worry about the 2x for a minute. Okay? Let's look at that as a theta. Okay? So if you have a sine theta that is equal to root 3 over 2, I still have to find my related acute angle first. Okay? So let me just find the related acute angles by taking the inverse of the root 3 over 2. So again, the opposite is root 3 and the hypotenuse is 2. Then we know that the related acute angle must be a pi over 3, which is a 60 degree. Okay? A 60 degree. So in quadrant 1, okay, so my principal angle theta, okay, so what is my theta? Well, the 2x here. Right now, I'm going to call this my theta, okay? In quadrant 1, it's the same as the related acute angle, so which is a pi over 3, okay? But in quadrant 2, my theta is going to be equal to pi minus the pi over 3. So that will give me 3 pi, so it's a 2 pi over 3. Okay? Now, what we are trying to solve is not the theta. We're trying to solve for the x. Okay? So this is the important part here. Once we know what the theta, like the angle, whatever that comes after the sine, that angle is equal to pi over 3 in quadrant 1 and 2 pi over 3 in quadrant 2. Then now I can solve this 2x because theta, if theta is equal to pi over 3, that means 2x, that 2x is equal to pi over 3, right? So when the 2x is equal to pi over 3, when I solve for the x, all you have to do is multiply both sides by a half, okay? So when you do that, you get a pi over 6, okay? A pi over 6. Now, same thing down here. My theta is 2 pi over 3 in quadrant 2, but in fact, theta is 2x. So when you set 2x is equal to 2 pi over 3, and then you can solve for the x by multiply a half on both sides, so you get a 2 pi over 6. Okay? Which will reduce it to a pi over 3. Okay? But this is not the only solutions. Okay? Why? Well, because the given range, the given domain here is between 0 and 2 pi. Okay? And think about this is only a 30 degrees, and this is only a 60 degree here. Okay? If you look at a sine of a 2x, okay, the tricky part here is because when sine 2x, since times 2x has the k values that is equal to 2. Okay, so that means, therefore, the period for this particular questions, the period is 2 pi divided by the k, so the period is only a pi. Okay, so that means when the x is between 0 and 2 pi, that means within that given domain, and if the period is only a pi, that means I will have 2 cycles that is happening within this given domain. Okay, because this question sine 2x only has a period of pi. So 1 pi give you 1 period. So between 0 and 2 pi, that means you will have 2 periods in it. So what I will have here, okay, when you got the answer for each of the quadrants for x, so for example, in quadrant 1, you have x that is equal to pi plus pi over 6. If you are adding another period, so that means from this solutions, when you add a pi in it, then you will be getting another answer. So 6, so that will give you a 7 pi over 6. Okay? So a 7 pi over 6 is also one of the solutions. Well, what is 7 pi over 6? Well, this is 30, 30 times 7. So this is a 210. So 210 degrees still within this given range. Well, this is 30, but when you're adding, going for another cycle, 180, you get 210, still within this given domain. So besides pi over 6, you also get 7 pi over 6 for the quadrant 1. Same thing here. When x is equal to pi over 3 in quadrant 2, but when you're adding a pi, because this period is a pi, so when you go around one more round, you will be getting a 4 pi over 3. And a 4 pi over 3 in degree is a 60 times 4 is 240. So 240 degrees still within that. But if you keep adding another cycle on here, it will surpass the 2 pi, which is the 360. If you're adding another pi here, it will surpass the 2 pi. So we're going to stop here. So for this particular questions, you will have 4 solutions. One is pi over 6, pi over 3. But when you're adding another cycle or another periods with the existing, and if those answer does not still within the given domain, then you will have another solutions for it. So you have 1, 2, 3, and 4. Okay? So this is the kind of question that you have to pay attention to when you're solving a trig equation that involves the double angles. Okay, if this double angle, that means the period has been shortened. If this is 3, that is even shorter. But if this sine 2x, instead of a sine 2x, you might be getting like a sine half x, then the period will get expanded. Okay, and so on and so forth.